Alright, so for part D, we are to find the average velocity of the particle for the time period from 0 to 6. So let's go ahead and write down the formula first, and then we'll go ahead and find out what the average velocity is. So the function that we're given is the velocity function. So do you remember how to find the average value of a function? Let's write down the formula for that first. The average value of a function, AV of f, sometimes is written as f average, is given by the formula 1 over b minus a times the integral from a to b of f of x dx. Okay? This is the average value. There's another formula known as the average rate of change, and they are connected. The average rate of change of the antiderivative of a function is the same thing as the average value of a function. All right, so they basically are similar. So this expression right here, you can also look at it as the average rate of change of the antiderivative, okay, which is going to be on the same interval, of course, f of b minus f of a divided by b minus a. So this 1 over b minus a is this piece right here, and then this integral is basically f of b minus f of a using FTC part 2. So they're basically connected. If the problem asks us to find the average rate of change of the displacement from 0 to 2, is the same thing as finding the average velocity from 0 to 6. Okay? So we don't really need this piece. We can just use this formula right here to figure it out. All right. So in this problem, we're looking for the average of the velocity function. Okay. So the average of the velocity function from 0 to 6 can be given by 1 over 6 minus 0 times the integral from 0 to 6 of the velocity function, which is 3 cosine e to the 2t over 3 plus 1. I'm not sure. Let me go up and check. Make sure I did that right. Look at the original problem. 3 cosine e to the 2t over 3 plus 1. Okay, good. So this is what we're looking for. The definite integral of this expression dt. All right. Okay, so this problem that we're doing is a calculator, open a calculator live problem, so you're free to use a calculator for this problem. If you weren't permitted to use a calculator, then you have to use the techniques of integration to evaluate this definite integral, and then you multiply it by 1 over 6. Since calculators are allowed here, we're going to take advantage of that. Now what I'm going to do is I'm going to go to the initial function we graphed in problem when we're doing the part A. I already entered it in my calculator, so I don't want to waste time to enter this function again. So what I'm going to do is I'm going to cut. Okay, we have a clipboard in our TI-89 titanium, which is a nice feature. So I'm going to use, well, let me just copy, okay? Diamond upward arrow will copy the function I stored in y1 into my clipboard, and I'm going to go to the home screen and I'm going to enter this expression. All right, so we have 1 over 6 times the integral. If you're not using a TI-89, if you're using an 83 or 84, you use the numerical integration function to evaluate this expression. Okay, that's fn int. You can find that in your catalog. All right, so we have the integral of the function, enter the integrand. We have it in our clipboard, so let's just diamond and paste it here. So there you go. The variable of integration is x. Our lower limit is 0. Upper limit is 6. All right, so there goes your answer. 0.733429. So it took my calculator about 2 minutes to compute that. Anyway, let's go ahead and write that down. So that's the average velocity. All right, average velocity. We have to be accurate to 3 decimal places. So it's 7342. So it's approximately 0.7342. Another thing you want to keep in mind when entering an expression in your calculator with a TI-89 is always make sure that the display, the pretty print, in the TI-89 is consistent with your entry, okay? So 1 over 6, and it go from 0 to 6, 3 cosine e to the 2x over 3 plus 1. So it matches so that we're confident our answer is in fact correct, all right? Okay, so let's move on to the E part. Okay, let's take a look at the E part. For the E part, we have to find all values of t in the interval from 0 to 2, for which the speed of the particle is 1. I made a change to the domain here in order for us to be able to solve the problem, okay? So this is slightly different from the original question. Okay, so let's go ahead and write down some information that we can use to solve this. If the speed is 1, what does that mean? So part E, if the speed is equal to 1, that implies that the absolute value of the velocity, which is also equal to the speed, is equal to 1, right? So that means that plus or minus velocity is equal to 1, and this implies that our velocity is plus or minus 1. Okay, so if the speed is 1, that means velocity is plus or minus 1. So the question is, at what times is our velocity plus or minus 1 on the domain 0 to 2? So how do we do that? So all we just have to do is you're going to enter the graph. We're going to draw the graph of the function and find the 2 times when our velocity is equal to 1 or negative 1 on the domain 0 to 2. Okay, so let's go ahead and graph our function. Let's see. Here. Okay, so we had the other 2 functions selected before. So if you want to deselect the acceleration function, just press F4. This is the only one we are graphing. So we're graphing it from 0 all the way to 2. Okay, so let's adjust our window. So diamond F2, our minimum x value is 0, maximum x value is 2. That's the only window we care about, so let's go ahead and graph it. All right, so there goes the graph on the specified domain from 0 to 2. Okay, so when does this function, the velocity function, attain a value of 1 or negative 1? How do we do that? All we just simply do is we're just going to graph the 2 horizontal lines, 1 and negative 1. Okay, so we're going to graph 1, enter, and negative 1. We're going to graph those 2 lines. Let's go ahead and graph it. There goes 1, and there goes negative 1. This is one way of doing the problem. Another way of doing the problem is just enter, instead of graphing this function, you graph the absolute value of that function, and then you just graph one line to find the intersections, okay? So this is one way of doing it, not the only way. So I need to find the value of this intersection and this intersection, and I don't know if that intersection is in the window. Then we can go from there. Okay, so let's start with the last one right there, F2. Let's trace when x is 2, enter, y is negative 1, so it's kind of beneath. So that's good. That's not a there's no intersection happening there. So let's go ahead and find this value of this intersection here. How do we calculate the intersection? You go to the math menu, F5, calculate intersection 5. It's going to ask you which curves you're looking at. So curve 1, of course, is the velocity function. Curve 3 is y equals 1. Enter. Lower bound is a point to the left of your of the intersection. Let's just use 0. And then the upper bound is a point to the right of your intersection. Right there. Enter. 0.6774. Okay, so that's the first time that that we have a speed of positive 1 when t is equal to 0.6774. 0.674. Remember, you have to be accurate to 3 decimal places. All right, t equals 0.6744. Is that 774? Is that the only time that we have a speed of that's equal to 1? No. When the velocity is -1 or the speed is 1 right here, we also have another time that meets the criteria. So let's find the intersection here. So we're going to go to F5 again, and we're calculating intersection. First curve is 1, enter. Second curve is the fourth function we entered, which is the line, y equals -1. Lower bound, a point to the left of the intersection, that's good. Upper bound, we're going to go to a point to the right of the intersection. Enter. T is equal to 1.2497, okay? 1.2497, okay? So these are the times when the speed is equal to 1, okay? So let's just write down a notation. These are the times when the speed is equal to 1. Remember what that means. That means the velocity is plus or minus 1. Okay, let's move on to the F part. So the F part, we have to write an expression involving an integral to give the position s of t, and we have to use the expression to find the position of the particle at t equals 3. So writing an integral expression for the position. All right, so to write the expression for the f part of an integral to give the position and use it to find the position at t equals 3, we need to write down a formula first, a formula for how to generate the position of our particle at any arbitrary time t. Okay, now that one involves calculating an integral, but it's different from the distance traveled. This is a position. Okay, so when we're calculating position, we have to remember that the initial position of the object should be taken into consideration also. So our position function s of t is equal to the original position of the particle. S of 0 was, what was S of 0 again? Let's go back and see what it was. S of 0 is 20. You can see here S of 0 is 20. That must be included since this is a vector quantity we're dealing with. So we have the original position 20 plus the integral from 0 to any arbitrary time t of the velocity function. Let's call it v of x dx. Oops, dt, sorry, dx. V of x dx. All right. So note that this is different from total distance. Okay, total distance is just the absolute value of the velocity on the time interval, but for position, you have to include the initial position plus the net change in position over the time interval. Okay, so this is the expression. Just setting this up alone in the AP exam will give you a point. Now we're going to use it to find the displacement after 3 seconds. Okay, so to do that, the second part, we're going to be basically looking for s of 3, which is equal to 20 plus the integral from 0 to 3 of our velocity function, which is 3 cosine e to the 2 t over 3 dt. All right. Okay, so the reason why I change these variables here is that I just want to keep the variables disparate. So now that I have a constant here, I reverted back to my t variables. Okay. All right. So now that we have this set up, remember this is a calculator portion. We can use our calculators to evaluate this definite integral plus 20. Okay. So let's go ahead and do that. Let's go home. I have this expression in here before, so I'm just gonna make some slight adjustments so I don't have to enter the whole thing again. So we just take out the 1/6, we have 20 plus that, plus this expression right here from 0 to 3. Enter. All right, so there goes your answer right there. And then what you want to do is you always want to cross-check your entry with what you have in your calculator. The original function v of t that I entered before had a +1 there, so let's put it back as a +1 dt. I found that out by comparing my result with what was in the calculator, and it didn't match. So let's see, 20 plus the integral from 0 to 3, 3 cosine e to the 2t over 3 plus 1. Good, so 21.9753, that's the position at t equals 3. Okay, so 21.9753. All right, now let's take a look at the last question, question G. I made a slight change to that one also. It says, find all times t in the interval from 0 to 2 where the particle changes direction. Okay, find the position of your particle at these times. All right, so let's go ahead and find where the particle changes direction. So we can do this graphically, part G. So before we do that, how do we know that the particle changed direction? The particle changes direction when the velocity changes from positive to negative. Okay, so let's write this down. The particle changes direction when the sign of the velocity changes. When the sign of the velocity changes. Okay, do not forget that the sign of the velocity tells you the direction of the object. So if it's positive, it's going to the right. If it switches to negative, then it's going to the left. Okay, so we're looking for sign change in the velocity. All right, so let's go back to the graph. We're going from 0 to 2 again. So let's go back to the function. I don't need, let's take that out. I don't need this anymore. I don't need that anymore. So we just need this function, and the window is from 0 to 2. Good. Let's graph it. So here where it's positive, the object is moving to the right. There it's not moving, it stops, and then it starts moving to the left, because the sign of the velocity tells you the direction of the object. Now, when does the particle change direction? It happens where the velocity function changes from positive to negative or negative to positive. So there's only one sign change here. So what we have to look for here is the 0 or the x-intercept of our velocity function. So how do we do that? We go to the F5 math menu again and look for 0. All right, remember 0 in pre-calc. That's what we're looking for here. 0, press enter. Lower bound any point to the left of the 0. We have only one 0 here. Enter. Upper bound any point to the right of that 0. Enter. 0.971152. So that's where the particle changes direction. So t, so let's write down the statement. At t equals 0.971152, the particle changes direction. The particle, in most cases, you'll be asked to justify your reasoning as to the change in direction here. So that's what I'm about to do. The particle changes direction. Since the velocity changes sign. Changes sign from negative to positive. From positive to negative, sorry. Changes sign from positive to negative. At t equals 0.971152. Okay? And also we're asked to indicate the position. What was the position of the particle at this time. So let's find the position of your particle at this time. Remember, we have already generated a position function in part F. That's a position function there. So we're going to use it again, okay? So let's write down the position function first, and then we're going to apply it. So the position of our particle at any time t, S of t, is given by the initial position, 20, plus the net changing position from 0 to any arbitrary time t of v of x dx. Okay, so that's our formula. We're going to be applying it to this situation right here. So we're looking for S of 0.971152. So that's going to be 20 plus the integral from 0 to 0.971152 of our velocity function. Hopefully I can get it right this time. Cosine e to the 2t over 3 plus 1. Don't want to forget that. dt. Okay? Alright, so let's go ahead and calculate what that is. Go home. We already have it set up for the original problem when we were doing the other part. So all we just have to do is change our limit of integration from 0 all the way to 0.971152. Enter. 21.4333. So this was the position of the particle when it changed direction. Okay, so let's write down what this remark means. The position of the particle when it changed direction is 21.4333. All right, so that's that. So thanks so much for taking the time to watch this presentation. You can feel free to subscribe to our channel. Please post a comments to let us know what you think about this clip. More clips can be found on mathgodserve.com/calculus. Thanks again for watching, and